So we've got two charges in this problem, Q1, which is located at the origin, and it's negative 4.5 nanocoulombs. And then we have charge Q2 over here, which is also negative, and that's negative 6.3 nanocoulombs. And these guys are 44 centimeters apart. And we want to know the electric field up here at this point, which is 25 centimeters away from the origin. Okay, so let's see. The electric field due to charge Q1 is going to point down like that, because it's attractive toward Q1, and then the electric field due to charge Q2 is going to point over toward Q2 like that. Okay, now this distance can be found from the Pythagorean theorem. We'll call that R2. R2 is the square root of 0.44 squared plus 0.25 squared, so that's 0.506. Okay. We're also going to need this angle here, theta, when we add up the vectors. Well, that angle theta is the same as this angle theta over here, and that is inverse tangent of opposite over adjacent. So that's 29.6 degrees. Okay, so we'll be using that later. Okay, so let me calculate the magnitude of each of these two vectors. The magnitude of E1 is going to be KQ1 over R1 squared, so I'm leaving off the minus sign here, right, because we're just asking for the magnitude. I've already decided the direction is down, and I'll use my standard Cartesian sign conventions. So I'll give this a minus sign later on. The distance 0.25 squared, so this is 648 newtons per coulomb in the minus y direction. Okay, and then E2, you can calculate that pretty easily, I think. We're going to use 6.3 times 10 to the minus 9, again, just using the positive value of the charge, the magnitude of the charge. We're going to use 0.506 for our distance that we calculated up here. That gives us 221 newtons per coulomb in a direction 29.6 below plus x. Alright, so to add these two vectors, we've got to calculate the magnitude, or we've got to break them into components, right? So E1x is just 0, and then E2x is, well, let's see, that's going to be 221 cosine of 29.6. That's 193. Alright, E1y, that's 648 in the minus y direction, so that's just minus 648. There's my negative sign. And then E2y, that's also in the minus y direction, right? Here's E2x. And here's E2y. So that point's in the minus direction, so that's minus 221 sine 29.6, so that's negative 109. Okay, so now I add them up, and I get my well, I guess I'm adding these up, aren't I? I usually do this a little differently. Okay, so E1x plus E2x is equal to my total electric field vector in the x direction, and that's 193. And E1y plus E2y is my total electric field vector in the y direction. That's minus 648 minus 109, so that's minus 757. Okay, so now I have the components of my x and y. So if I make myself a little coordinate system here, I have that my total x electric field is plus 193, and my total y is minus 757. So my vector is going to be down here. Probably should just call this 757. Okay? Going to make some angle alpha with respect to the positive x-axis. Okay, so now I just have to solve for the hypotenuse of this triangle, right? So the E total, the magnitude of E total is square root of 193 squared plus 757 squared. So that's 781. And then alpha, that's going to be the inverse tangent of opposite over adjacent. Notice I did not use the minus sign there for the 757. I've already decided that alpha points below the plus x-axis. Pointing below means that it's going to have a negative to it. I don't need to add that in here. I'm just trying to find alpha. I'm trying to find an angle, a number between 0 and 90. It gives me 76 degrees. Okay, so my final answer is 780 newtons per coulomb at an angle of 76 degrees below plus x.